Welcome to another deep dive. You sent over a massive stack of developer docs, textbook chapters, and framework guides asking us to finally demystify one of the most notoriously frustrating, hair-pulling errors in all of web development.
Oh, absolutely. The dreaded red console text.
Exactly. So today, our mission is to break down CORS cross-origin resource sharing specifically for your workflow. We're going to explore what it actually is, and just as importantly, what it isn't.
Right.
We'll unpack the underlying trust model, the mechanics of simple versus pre-flighted requests, how to actually implement it in frameworks like Spring and Express, and finally, how to systematically debug those errors.
It's going to be a packed one.
It really is. Now, if you enjoy deep technical breakdowns like this, make sure you subscribe to our YouTube channel, The Daily DevOps, and also subscribe to our newsletter, CoreCraft, where we share deeper insights, tools, and learning resources.
It's great to dive into this. CoreAs is one of those topics that almost every developer encounters, usually right when they think a feature is finally ready to ship.
Always at the last minute.
Exactly. But what's fascinating here is that CORS isn't actually a bug. And it's certainly not a server failure. It's a fundamental security mechanism of the modern web. Once we understand the rules it plays by, it stops being this mysterious obstacle and, starts making perfect sense.
Okay, let's unpack this from the very beginning then. To really understand CORS, we have to start with the concept of an origin and the same origin policy.
Yeah, that's the foundation.
Without this policy, the web would essentially be the Wild West. Any website you visit could just openly exploit your active sessions on other websites. But before we get into the exploits, we need to define the boundaries. What exactly counts as an origin?
So the browser defines an origin very strictly. It consists of exactly three parts. You've got the protocol, the domain, and the port.
Okay, protocol, domain, port.
Right. If any single one of those three components is different, the browser considers it a cross-origin request. For instance, HTTPS versus HTTP, that's a different origin because the protocol changed.
Makes sense.
And ap.example.com versus just example.com, different origin because the subdomain changed.
And we've all fallen for this classic developer trap at least once. Spinning up the front end on http.localhost.12000 and the back end on http.127.0.1.55500.
Oh, yeah. The classic.
You completely forget that the browser sees those as distinct origins. To us, localhost and 127.0.0.1 mean the exact same thing our own computer, but the browser flags it immediately.
It's basically a developer rite of passage at this point. The browser defaults to the same origin policy, which dictates that JavaScript running in a tab is only allowed to read responses from the exact same origin it was loaded from.
Right.
If it tries to reach out to a different origin, the browser intervenes. To understand why this is so critical, let's look at a classic trust model scenario. Imagine you're logged into your bank's website. You have an active session, meaning your browser is holding onto a session cookie for that specific bank domain.
Right, so the browser knows I'm authenticated.
Exactly. And while that tab is open, you open a new tab and accidentally visit a malicious site.
Oh.
Yeah. That bad site contains hidden JavaScript. Because your browser is executing that JavaScript, the script can command the browser to make a POST request to your bank's transfer endpoint, attempting to send money to an attacker's account.
Wow.
And because your browser still holds that active session cookie for the bank, it automatically attaches that cookie to the outgoing request. The bank server receives the request, sees your valid cookie, and assumes you authorize the transfer.
That is a terrifying scenario. But wait, I want to clarify something here because we hear a lot about CSRF cross-site request forgery. Isn't that what you just described? Where does CORS actually fit into that?
That's a really great distinction to make. What I just described is indeed a CSRF attack. The defense against that is server-side. The server requires a unique CSRF token that the malicious site couldn't possibly know, so the server rejects the transfer.
Okay.
CORS, on the other hand, operates on the response side of the equation.
And here's where it gets really interesting. This is the massive aha moment for a lot of people dealing with this. CORS does not block requests from reaching the server.
Exactly.
In that bank scenario, the malicious request from the bad site actually still happens. The browser sends it, and the server receives it. What CORS does is act like a security curtain. The browser refuses to let the malicious JavaScript read the response that comes back.
This raises such an important question about how we view browser security. The request goes through. If the server isn't protected by other means, like those CSRF tokens we just mentioned, it might even process the transfer.
Which is wild to think about.
It is. But the browser prevents the malicious site from seeing if it succeeded, or reading your account balance, or grabbing any sensitive data from the response. This proves that CORS is strictly a browser-level protection.
Right, because if you use other tools,
Exactly. Tools like Postman, or curl in your command line, or a Python script, they don't enforce CORS at all. If you send that same request via Postman, it works perfectly. That disconnect is exactly why developers get so frustrated when an API works in Postman but fails in Chrome.
I love the analogy of a bouncer at a club for
No,
this.
that's a good one.
Yeah, so the browser's the bouncer. The JavaScript on the web page is a person trying to get information from inside the club, the server. The bouncer walks up to the club door, knocks, and says, "Hey, I have a guy from this other domain out here who wants to see what's going on inside."
And the server checks the list.
Right. The server checks its guest list, which is the access control allow origin header, and says, "Nope, they aren't on the list." The bouncer then turns around and refuses to tell the JavaScript anything about what's inside the club.
It's a highly effective way to visualize it.
Mm-hmm.
And if we connect this to the bigger picture of web security, CORS is a perfect example of defense in depth.
Yeah.
It's not a server firewall. It doesn't replace secure session management or authorization. It just adds a specific layer of protection against cross-origin data theft inside the user's browser environment.
So how does our bouncer actually check this guest list before letting a request through? Because the browser doesn't treat all requests equally, right? It divides them into two main categories: simple requests and pre-flighted requests.
That's right. Let's look at the simple requests first. The browser categorizes a request as simple if it uses the getHead, head, or post methods, and only utilizes very standard, safe HTTP headers, things like accept or content language.
Okay, the basics.
Yeah. For these simple requests, the browser sends the actual request to the server immediately. The server processes it and sends a response back.
And attached to that response, the server needs to include that VIP guest list we talked about, the access control allow origin header.
Exactly. When that response arrives, the browser inspects the header. If the header says access control allow origin, the wildcard, meaning everyone is allowed, or if it explicitly matches the origin that made the request, the browser drops the curtain and lets the JavaScript read the data.
And if it doesn't?
If the header is missing or doesn't match, the browser triggers the core error and hides the response entirely.
Okay, that handles simple requests, but what about the other category? The complex or pre-flighted requests. If I'm trying to send a per-to request to update a database record, or a delete request, or even just a standard GET request, but I attach a custom header, like an authorization token, the browser hits the pause button.
Right.
It doesn't send the real request right away. Instead, it sends an options request first. This is the pre-flight. But why do we even need this?
Well, it does this because a delete or put request inherently changes data on the server. Think back to our rule for simple requests. The request actually reaches the server before the browser checks the response headers.
Oh, I see.
If the browser just blindly sent a cross-origin delete request, the server might process it and delete a user's data before the browser ever had a chance to realize the origin wasn't allowed.
So the pre-flight is literally the browser asking for permission before it does anything destructive.
Yes. It sends that options request to explicitly ask the server, hey, is it okay if this specific origin sends a delete request with these specific custom headers? The server evaluates that pre-flight and responds with its permission headers.
Like saying what's allowed.
Exactly. It sends back access control allow methods to declare which actions are permitted and access control allow headers to approve any custom headers.
And only if that pre-flight gets a thumbs up does the browser actually send the real delete request. That makes total sense. But it brings up a historical quirk from the sources that I found really fascinating. Why is a POST request considered simple and allowed to hit the server immediately, while a PET request is considered complex and requires permission first? Both of them can alter data on the back end.
It all comes down to legacy web standards and backwards compatibility. Long before CORS or modern single-page applications existed, basic HTML form tags have always been able to send POST requests to any website on the internet. It was a fundamental feature of the early web.
Oh, right, like submitting a contact form.
Exactly. Because of that, back-end servers historically always had to be built to handle the risk of receiving random post requests from anywhere.
They had to build their own defenses, like those CSRF tokens.
Precisely. So when the core standard was formalized, the architects couldn't just suddenly start blocking all cross-origin post requests, or they would have broken half the internet overnight. They had to classify post as simple to keep the web running.
But Putin delete didn't have that baggage.
Right. Put, patch, and delete methods were not traditionally used by simple HTML forms. They were heavily adopted later for REST APIs.
Mm.
Because there wasn't a massive legacy footprint of cross-origin 2UT requests, the browser could safely demand a pre-flight check for those newer methods without breaking existing websites.
You know, it's wild how architectural decisions made decades ago still dictate the exact network traffic our browsers generate today.
It really is.
Quick reminder, if you're enjoying this deep dive, subscribe to the Daily DevOps YouTube channel and our CoreCraft newsletter for more content like this.
So we've got the theory down.
Yeah, we have a solid grasp on the theory. The browser checks the server's headers, and sometimes it has to send a pre-flight request to ask permission. But how do we actually implement this in the wild? How do developers tell the server to send the right CORS headers? Let's look at two massive frameworks, Spring Boot for Java and Express for Node.js.
Let's start with Spring Boot. Historically, configuring web security in enterprise Java could be, well, quite tedious, but modern Spring handles this very elegantly. You can manage CORS at a granular level by dropping a cross-origin annotation directly onto a specific controller method.
That sounds easy.
It is. You can specify the exact origin right there, like allowing only http.localhost.9000.
But what if you have a massive API with dozens of endpoints? You wouldn't want to paste that annotation on every single method, right?
No, definitely not. For larger applications, Spring allows you to set up a global CORS configuration by implementing the WebMV configurer interface. You can define mappings that apply to your entire application, specifying allowed origins, methods, and headers, all in one centralized configuration class.
That's much cleaner.
It abstracts the manual HTTP header management entirely away from the developer.
Ah,
Though you do have to be careful with edge cases.
like what?
Like ensuring your allowed origins don't include a trailing slash if the requesting origin doesn't send one. That's a surprisingly common configuration mismatch.
Oh man, that trailing slash issue is exactly the kind of invisible bug that drives people crazy. We see a very similar philosophy in Express for Node.js. They have a widely used NPM middleware package simply called CORS.
Right, very straightforward.
Yeah, if you just write app.useCORS, it automatically adds the headers to allow all origins by default. That's fantastic if you're building a public API that anyone should be able to query.
But for a private API or a software as a service platform, you need strict control. That's where Express provides immense flexibility. You can pass a dynamic function to the origin option in the middleware.
How does that work?
When a request comes in, that function can take the origin of the request, run logic like checking it against a database of paying tenants, and dynamically decide whether to allow it or reject it on the fly.
That sounds incredibly powerful, but it also sounds like a place where things could go really wrong. I know developers sometimes use regular expressions to dynamically match origins, like trying to allow any subdomain of their company.
And that introduces a significant security vulnerability if not done perfectly.
Yeah.
Let's say a developer writes a custom regex in their Express CORS configuration to allow .yourdomain.com.
Okay.
If the regex isn't strictly bounded, an attacker might register a domain like hackyourdomain.com, which technically matches the poorly written regex.
No, because your domain is just a substring in there.
Exactly. Suddenly, the server is serving up access control allow origin.https.hackyourdomain.com, and the attacker has full read access to your API. Dynamic origin checking is powerful, but it requires rigorous testing.
That's a huge trap to watch out for. We banter about how easy these frameworks make it look just one annotation or one line of middleware, but it contrasts so sharply with the immense frustration we feel when the configuration is slightly off. So what does this all mean when we're staring at that dreaded wall of red text in the browser console? What are the common buckets these errors fall into?
Debugging CORS usually boils down to four main categories. The first is simply a missing access control allow origin header entirely. This usually just means the backend developer forgot to enable CORS middleware, or the API gateway isn't configured to pass the headers through.
Okay, that's the most basic one. What's the second?
The second error is a mismatch. The header is present, but it doesn't match the origin that made the request. For example, the front end is running on localhost bot 3000, but the server is hard-coded to only allow production.com.
And then there's the local file testing issue.
Yeah, that's the third common error, making non-HTTP requests. If you're building a simple static site and you just double-click the HTML file on your desktop, it opens in the browser using the file protocol. CORS strictly requires HTTP or HTTPS protocols. The browser will often trigger immediate CORS errors for local file testing because a file origin is considered null or opaque.
Got it. And the fourth one.
returning multiple allow origin headers. The browser expects exactly one value. This frequently happens in complex deployments. Let's say you have an Nginx reverse proxy sitting in front of an Express backend.
I can see where this is going.
Yep. The developer configures Nginx to add the CORS header and also configures the Express app to add it. The browser receives a response with two identical headers, panics, and blocks the response entirely.
I think every developer has spent hours debugging an app only to realize their proxy server was duplicating the headers. But here is where things get really tricky. The credential trap.
Oh, this is the big one.
Let's say your front end needs to send an authentication cookie to the back end. So you set credentials, include in your JavaScript fetch request. You might think, I'll just set my back end to allow the wildcard origin, the asterisk, so my front end can connect from anywhere. If you do that, the browser will outright reject it.
It's a critical security feature built into the specification. If a request includes credentials like cookies, authorization headers, or TLS client certificates, the browser absolutely refuses to accept a wildcard for the allowed origin.
No exceptions.
None. It demands that the server specify the exact, explicit domain it is granting access to. Furthermore, the server must also explicitly send the header access control allow credentials.
Sure. Why is the browser so incredibly strict about that specific combination?
Think about the massive privacy risk. If a server allowed any random website on the internet to read its data using a wildcard and simultaneously allowed browsers to attach user cookies to those requests, it would be a catastrophic breach.
Wow, yeah.
Any site you visit could secretly pull your private, authenticated data from other services where you are logged in. The browser forces developers to be explicitly intentional when credentials are in play.
That makes a lot of sense. Now, what if a server actively wants to reject a request? I read about a really clever security practice regarding this. Instead of just sending back an empty header or no header at all, the server might send back a fake domain like does.not exist in the allow origin header.
Yeah, returning a fabricated domain is a great application of the principle of least privilege. By returning does.not exist, you guarantee that the header will never match the real requester's origin, ensuring the browser blocks the read operation.
And it hides your actual configuration.
Exactly. You aren't leaking any information about which domains actually are on your approved guest list. It keeps potential attackers completely in the dark about your infrastructure.
So when you are actually in the trenches staring at a broken app, what are the best tools to figure out which of these rules you broke? The Network tab in your browser's developer tools is obviously the first stop to look at the execs, request, and response headers.
Always start there.
But I've also seen developers using interactive explainers like Will It CORS, which walks you through the logic step by step. And for advanced debugging, using HTTP interceptors like HTTP Toolkit or Questly.
Those interceptors are fantastic assets. They allow you to pause network traffic and modify headers on the fly. You can inject the missing CORS header locally into the response before it hits the browser engine and see if your front-end application actually starts working.
That is so useful.
It really saves you from having to constantly recompile and redeploy your backend code just to test a CORS configuration tweak.
Speaking of local testing, developers sometimes get desperate. We've all seen the Stack Overflow answers suggesting you intentionally disable Chrome's web security flags via the command line or install proxy extensions that aggressively strip all CORS headers away so you can just keep working on your front end.
We really need to emphasize the danger there. You must be incredibly careful with those bypasses. Disabling your browser's web security removes all same origin protections across the board.
That sounds risky.
It is. If you use that same browser instance to check your personal email or log into your bank while you're working, you are leaving yourself wide open to cross-site scripting and data theft. Those hacks should strictly be used in isolated, temporary development environments, like a dedicated browser profile, and never ever for regular browsing or production environments.
A stern but absolutely necessary warning. Okay, we have covered a massive amount of ground today. Let's recap the major insights. CORS is a browser-enforced security measure, not a backend firewall. Origins are strictly defined by the combination of protocol, domain, and port.
Right.
Requests are divided into simple ones that go straight through, and complex ones that require a pre-flight options check to ask permission first. And modern frameworks like Spring and Express have built-in tools to manage these response headers, though you have to be careful with the dynamic configurations and credentials.
And if there's one recurring theme to pull from all of this, it is that CORS is fundamentally about protecting the user's browser data. It prevents a malicious website from using your browser as a puppet to read your private information from other servers. It is not designed to shield the backend server from unwanted network traffic.
Yes. If there is a single, most practical takeaway to burn into your memory from this deep dive, it is this. CORS decides who can read, not who can send. The request almost always hits your server, but CORS decides if the JavaScript on the web page is allowed to see the answer.
And if we connect this to the bigger picture, it's fascinating to see where web development is heading next. With the massive rise of server-side rendering frameworks like Next.js, the paradigm shifts entirely.
How so?
When your Next.js server makes an API call to your backend, it's a server-to-server communication. The browser isn't involved in that specific fetch request at all. Because the browser isn't there to enforce the same origin policy, CORS completely vanishes from the equation. It forces us to constantly adapt how we think about security depending on where our code is actually executing.
That is a fantastic point to end on and a whole new rabbit hole for us to explore in the future. If this deep dive helped you understand the topic better, make sure to subscribe to the Daily DevOps YouTube channel and join our newsletter, CoreCraft, where we share deeper technical breakdowns and resources.
Thanks for listening.
Catch you on the next one.